Hello, class. Welcome to the Stat 312, Chapter 5, Part 1 notes. These set of notes are going to focus on inferences for two populations. You may recall in your Stat 211 and 215 courses that you did cover inferences for one and two populations. Our previous set of lecture videos focused on the one population. This Chapter 5 information will focus on two populations. Now, you may be saying, why should we study two populations? Well, when we do, there's really two motivations. We either want to compare two distinct groups, such as undergraduate and graduate students, or we have a desire to compare two partitions within a single group. For example, we often see this with drug trials, or sometimes we can see this in agricultural experiments. So when studying two populations, we have two main methods of collecting our data. First, we have what we call as independent samples. And this you'll see me abbreviated as TIS. That stands for two independent samples. And the methods we'll see this is we'll either see two completely separate groups, such as our undergraduate and graduate students. Or sometimes we will split a group into two groups and then compare them with a treatment 1 versus treatment 2. Next, we have dependent samples, and you'll see me abbreviate this as DS. And this is data that is going to be naturally paired. Now, this term may seem funny to some of you. What can naturally paired mean? We often use this expression when we're talking about before and after studies. If you think of any sports or skills that you've had to learn, you often hear the ideas of a pre-test and a post-test. That's what we're talking about when we say before or after studies are paired. You're not going to take a pre-assessment from one student and compare it to another student's post-assessment. You're going to care about the same student and compare that same student's pre and post-assessment. We also see this, although it is much harder to do, in identical twin studies. These two methods for collecting data require different inferential procedures and tools, meaning different formulas. We're going to start by focusing on the dependent samples. I do want to warn you, your book, I believe, starts with independent samples, but the notes are structured a bit differently. So to begin with, let's give you some examples of dependent samples. I gave you one earlier that before and after treatments. Another could be brother and sister experiments. And something more simple could be in taking an insurance quote from a local insurance company versus going online. For dependent samples, they are structured in a pretty particular way. You'll have your two samples, your before and after, structured into rows. And I'm going to put in some hypothetical numbers just to make it a little bit easier. So say I have a 10, 2, dot, 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 all the way to a 0, 5, a 3, dot, 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 all the way to say 4. So what we'll do is we'll have these two samples, our y1 and y2, and we can go ahead and we can take our mean, that is our y bar. So for our first sample, we would say that is y1 bar. Our second sample, we'd have y2 bar. And then we can also calculate their variance. So for our sample 1, that would be S1 squared, and for sample 2, that would be S2 squared. Now when we're doing two independent samples, this piece of information here is what we focus on. But when we're doing dependent samples, we care about the difference. That is y1 minus y2. So instead of focusing on these two individual samples, we focus on the difference at every single level. So in other words, if I were to subtract, say 10 minus 5, that's 5, 1 minus 3 is negative 1. We'd keep doing the differences. 0 minus 4 is negative 4. Now we have a new set of data based on our differences of our two samples, and we'll end up taking the mean of that, and we represent that with d bar. And then the variance of that sample is SD squared. These two statistics are what we are concerned about when we're working with dependent samples. And for us, when we're working with dependent samples, we're caring about the difference. Particularly, we care about the population mean of our pair differences. Okay, so let's take a look at this a little bit further and introduce you to some of our formulas. So when we're doing inferences on our mu-d with a dependent sample, there's first an assumption that we need to make, and that is that the sample can be paired, and its end inferences are a random sample from a normal distribution with mu-d. Once we can verify our assumption, we can then begin our analysis, such as taking the difference d of each pair and then using our chapter 4 inferences on mu with our sample mean d bar and our variance SD squared of our end differences. Now comes to the most important part, is how we actually can perform our inferences, and that's with the hypothesis test and confidence intervals. For dependent samples, we are not going to concern ourselves with a prediction interval. So for our hypothesis test, very similar process as we did for one sample. We'll begin with a two-line hypothesis. Our null hypothesis will be H naught colon mu d equals delta naught versus H1, which is our alternative hypothesis, where UD can either be less than, greater than, or not equal to delta naught, with our test statistic T equals d bar minus delta naught all over the square root of SD squared over n. And we'll compare this with the t distribution with degrees of freedom equal to n minus 1. We also have our confidence interval, which would be a 100 times 1 minus alpha % confidence interval for mu d, which is d bar plus or minus t alpha over 2 multiplied by the square root of SD squared over n, where we have a critical value t alpha over 2, which has a degrees of freedom of n minus 1. Now, what I do want to emphasize is that this statement of analysis, essentially what happens when we have a dependent sample, scroll back up for a second, is we have our two before and after treatments, our brother, sister, whatever it is, our two sets of data. Once we do that subtraction, we now have a single sample. And then once we have that single sample, we treat it just like we did in chapter 4, which is why, with the exception of having d bar instead of y bar and SD squared instead of S squared. That's the only difference. It's still following the t-distribution with degrees of freedom n-1, which is why I start with dependent samples, because it's kind of a nice transition between what you did with one sample and what we're now doing with two populations. So let's do an example, because I feel that theory is great, but sometimes you really need an example to understand what we're really doing. So this comes from our book. It's exercise 5.12. We have 8 samples of effluent from a pulp mill, which were divided into 10 batches. From each sample, 5 randomly selected batches were subjected to a treatment process intended to remove toxic substances. 5 fish of the same species were placed in each batch, and the mean number surviving in the 5 treated and untreated portions of each effluent sample after 5 days were recorded and given in Table 5.18. We want to test to see whether the treatment increased the mean number of surviving fish. Okay, so first off, we want to explain why this is a dependent sample, and then afterwards we can perform the appropriate paired t-test. That's what we like to call our test when we are working with dependent samples. We generally refer to them as paired test, or specifically paired t-test. Now, may not be naturally obvious that this is a paired sample, but really what it is that our treated versus our untreated comparisons are paired by the effluent sample. So now that we've established that these are in fact paired data, I'm going to scroll back up. We're going to need to prep this data a little bit. We need to get our differences. So we're going to kind of create this row underneath the original data table that'll give us our differences. And I'm going to do treatment versus untreatment, or subtracted from the untreated. I should warn you, I often abbreviate treatment as TRT. This is something I learned from my previous professors, and honestly, treatment is a pretty long word to have to write out a bunch of times. So, okay, so to begin, 5 minus 5 would be 0. 5 minus 1 would be 4. 1.2 minus 1.8 would be negative 0.6. 4.8 minus 1 is 3.8. 5 minus 3.6 would be 1.4. 5 minus 5 is 0. 4.4 minus 2.6 is 1.8. And 2 minus 1 is 1. I do want to clarify that I could have gone the other way, where I did untreated subtracted from treatment. The reason I didn't is I prefer personally to work with positive numbers as much as possible. So usually I'm going to subtract based on what's going to give me a positive value. And our hypothesis, although we haven't talked about it, is that the idea that we should have an increase in our mean with the treatment. So the treatment values should be higher, which means more of them should be greater than the untreated. So now that I have this new column of information, I'm now going to want to calculate my average, my d-bar, and my standard deviation, that SD squared. Now to save ourselves some time, I am going to do this in JMP. So I'm going to open up JMP, get rid of that tip of the day. One of these days I might actually read it, but we'll see. I'm going to go to File, Data Table. Yeah, I'm going to give this a name because I can. And actually, I'm going to start plugging in. Good. So now that we have our data, hopefully I've typed this in correctly, I'm going to go to Analyze, Distribution, pull my difference over to the Y comma columns, hit OK, and I'm going to be focusing on my summary statistics. Okay, so now that I have this information, I'm going to go back to my original slides, and I'm going to record my values. So my D bar is going to be 1.425. Now, of course, StatCrunch, sorry about that. I'm going to probably do that a lot during these videos. JUMP gives us the standard deviation. So we're going to need to square that value. Our standard deviation was 1.7219. We're going to go ahead and square that. We're going to get 2.9699. Okay, so now that we have the statistics we need in order to do our inferences, we can really begin doing our paired t-test. Now to begin, we are going to do our four-step process, which means step one states that we need to make our hypothesis. Our two-line hypothesis with nulls and alternative. We are working with a paired t-test, which means our parameter of interest is mu d. And afterwards, we are going to have an equal sign for our null hypothesis. Now, next comes our delta naught value. Generally speaking, when we are comparing two populations, this value is going to be 0 because we are trying to determine if there's any change at all. The only time you're going to see this value not be 0 is when we've already established that there is a difference, but we want to see if there's a change in that already determined difference. And if we go back to our original problem, as I stated before, we want to see if there's an increase in the mean number of surviving fish. So this is going to be greater than 0. So now we have our null and alternative hypothesis. Let me remind you, in this case, our D is treatment minus untreated. And ideally, we're saying that our treatment should be greater than our untreatment. Okay. So now let's begin by calculating our test statistic. Step 2. We know that our formula is T equal D bar minus delta naught over square root of SD squared over N. From our slide 6, we have that our D bar is 1.425. And we are going to subtract 0, take the square root of 2.9699, and double checking, we've got 8 samples. So divide by 8. Now we can plug into our calculator and get our test statistic of 2.34. Excellent. This brings us to our step 3. And we know that we are going to reject our null hypothesis if t is greater than t alpha. This is based on our alternative hypothesis being greater than, which means we now need to figure out what our t alpha is. Now we were not given an alpha value, and when we're not given an alpha value, that means we need to assume alpha is 0.05, and our degrees of freedom is going to be n minus 1 or 8 minus 1, which is 7. This will give us a t alpha value of, well, let's see, pulling up my t table. We have, let's see, 0.05 and degrees of freedom 7. So that's going to give us a critical value of 1.8946. If we compare our test statistic of 2.34 to our critical value of 1.8946, we can see that our test statistic is clearly greater than. So therefore, we will reject our null hypothesis, which, as statisticians, generally speaking, rejecting the null hypothesis is what is desired. So we're happy people right now. This brings us to our final and most important step, our conclusion. So we will say at 5% significance level, we reject the null hypothesis. There is sufficient evidence to infer a mean increase in the number of surviving fish. Very good. Okay, so that brings us to the end of this problem. Just to review, we did our 4 steps for our hypothesis testing. We stated our hypothesis, we calculated our test statistic, we made our decision and stated our conclusion. And that brings us to the end of really what I wanted to talk about as far as the dependent samples go. Now we can start talking about the 2 independent samples. Now, before we begin this section, I do want to emphasize something. There are a lot of formulas for 2 independent samples. I'm going to focus on one of 3 scenarios when dealing with 2 independent samples. I do not want to make these lecture videos any longer than necessary, so I'm going to leave you to go learn about the other 2. They're in your textbook. And what the other situations have to do is whether or not we know about the population variance. And I'll talk about that a little bit more in a couple slides, but I just wanted to give you a heads up now at the beginning of this portion of the video that I'm only going to cover one of 3 scenarios, and I'm going to leave you to look up the other 2, just because I don't want to have to make these videos longer than necessary, and the only added information is really the formulas themselves. Okay, so to start off talking about our 2 independent samples, no surprise, but not all samples drawn from 2 populations are dependent. In fact, majority of them are not. Some examples of this could be, say, seniors versus non-senior scores in this class. Another one could be if we have a group of students that are interested in going on a diet. We divide these into 2 groups, and we have group 1 do diet 1, and group 2 do diet to, and then compare the effectiveness of the diets. When we're doing two independent samples, we have 4 parameters of interest. We have 2 population means, mu1 and mu2, and then we have 2 variances, which would be sigma 1 squared and sigma 2 squared. Now, as a assumption, we do assume that sample N1 with its subjects are random from our first population, meaning it's an independent population 1 sampling, and our sample 2 subjects are also drawn randomly from a second population. And also we want to say that we want to make inferences on the difference between these two populations. So really what we care about, our delta, as we can say, is the difference between our two populations, or the difference between mu1 minus mu2. Or in some cases we'll do mu2 minus mu1. It doesn't matter which direction you go, same as with the paired, as long as you keep it consistent. Now, as we are caring about the difference between two population means, it might be a good idea for the point estimate to be the difference between their two sample means. Okay. So as I said before, I had some assumptions. I gave you the assumptions about the sampling of the two samples. Now we need to talk about a little more assumptions. I do apologize. This is a lot of typing on one slide, and I am going to read it. I don't actually have anything further to add than what is on these slides, but it is important to know the assumptions behind the formulas that we're using. So for population 1, we assume that y1, 1, y1, 2, all the way to y1, n1 are a random sample of size n1 from a normal distribution with population mean mu1 and variance sigma squared 1. We let y1 bar and s1 squared represent the mean and variance of this sample. All right, guys, I lied to you. I do want to draw your attention to this notation. So when we have a lowercase value, you know that means a single observation. So y is a single observation. And when we were working with one sample and we had y1, y2, y3, y4, it was to denote a particular observation in a single sample. What this is showing us is our first coefficient tells us what group we're in, group 1 or group 2, and then our second value, our second coefficient, gives us the individual observation in that group. So y12 says that this single observation is in group 1 and it's the second observation. For population 2 then, for its assumptions, we say y21, y22, all the way to y2n2 are a random sample of size n2 from a normal distribution with population mean mu2 and variance sigma squared 2. We let y2 bar and y2 squared represent the mean and standard deviation of this sample. Finally, the last of these assumptions. We must also assume that the sampling populations of 1 and 2 is done in a manner that is mathematically independent, meaning they're not dependent. In layman terms, this means that the sample of population 1 was drawn completely separate from that taken from population 2. Kind of like how the outcome of flipping a coin is irrelevant to the outcome of the next Super Bowl. Your coin flip and the Super Bowl are mathematically independent chance experiments. Okay, now going to these various situations for two independent samples. I'm going to read this lovely little paragraph and then we'll talk about it a little more. So chapter 5 presents a large number of cases for handling this problem. We are going to focus on the case where sigma 1 squared and sigma 2 squared are unknown but are assumed to be equal. So basically, when we're comparing two independent samples, there are three situations. There is a situation where sigma 1 squared and sigma 2 squared are known. There's the situation where sigma 1 squared and sigma 2 squared are unknown. But we assume that they're equal. And then the third situation is that sigma 1 squared and sigma 2 squared are unknown and believed to be unequal. I'm going to leave you to do 1 and 3 on your own, because generally what it is in these cases is you're going to read your scenario, you're going to say, all right, we've got two independent samples, you're going to look at your standard deviations. Do you have the population standard deviation? Okay, it's option 1. Use those formulas. More than likely, however, you are not going to be given the two population standard deviations. You're going to be given the sample standard deviation. So that'll draw you down to problems 2 and 3. And for us, we're generally concerning ourselves with the assumptions where our population standard deviations are not known, but we do assume that they're generally equal. And so when we have that situation, we have this common population variance sigma, because sigma 1 squared and sigma 2 squared are equal. And how we make a measurement of this is we do something called pooling the sample variance together. And we use this formula, SP squared, or also known as the pooled variance, and is equivalent to the quantity of N1 minus 1 and quantity S1 squared plus the quantity of N2 minus 1 and quantity squared multiplied by S2 squared all over N1 minus 1 quantity plus N2 minus 1 quantity. Sometimes if you're looking this up online, you'll see this simplified and rewritten as N1 plus N2 minus 2. That's honestly how I prefer to write it, but that's just me. One thing I want to say about pooling is that you guys know that there is a difference between what you sometimes learn in the classroom and then what you do in real life. In classroom studies, we tend to focus on the case that I'm focusing on with the pooled variance, where we assume that the population variances are equal. In the real world, more than likely, option 3 is what we're going to use more than often than not, because we can't assume that, because we don't know for sure. But again, this is a classroom. This is the land where things can actually magically be perfect. And so for that reason, this is the one that statistics textbooks really focus on, if you're wondering why we would pick this scenario as to one that may not seem as logical as some. All right, so going back to our slides, so we use this pooled variance to calculate our hypothesis test and confidence intervals. To get to our formulas, our hypothesis test is, as always, a two-lined hypothesis where our null hypothesis is delta equals delta naught. Delta equals mu1 minus mu2. I personally prefer to see the mu1 minus mu2. I think it makes the problem easier to understand. If you put delta, I'm not going to mark you wrong, but it's my personal preference. And so as I said, we have our two-line hypothesis, we've got our null hypothesis, and our alternative hypothesis. Our two-sample test statistic is T equal to the quantity of y1 bar minus y2 bar minus our delta naught all over the square root of our pooled variance multiplied by the quantity of 1 over n1 plus 1 over n2. and we will compare it to the t-distribution, and this is a change from what you've seen before anytime we've used the t-distribution, with degrees of freedom n1 plus n2 minus 2. And then we will have our corresponding confidence interval, which will have the formula of y1 bar minus y2 bar n quantity plus or minus t alpha over 2 multiplied by the square root of sp squared multiplied by the quantity of 1 over n1 plus 1 over n2 n quantity. And once again, we'll be using that t alpha over 2, and our degrees of freedom will be n1 plus n2 minus 2. Okay, so to conclude this first part of our Chapter 5 video, let's go ahead and do some practice using our two independent sample knowledge. So to assess the effectiveness of a new diet formulation, a sample of 8 steers was fed a regular diet, and another sample of 10 steers were fed a new diet. The weights of the steers at 1 year had a sample mean and sample standard deviation of 845.5 and 43.283 for the regular diet, and a sample mean and sample standard deviation of 904.6 and 36.728 for the new diet. Is there sufficient evidence at the 5% level to infer that the new diet yields a higher population average weight? Okay, so to begin, I think it's just good practice to write down what information we know. So to do that, we have two samples, our sample 1 and sample 2. I'm going to say sample 2 is going to be our regular diet and sample 1 is going to be the new diet. Again, I prefer to keep things positive, which means I'm going to do 1 minus 2, where 1 is the value I believe is larger. So that means our regular diet had a sample size of 8, a sample mean of 845.5, and a sample standard deviation of 43.282. Our sample 1, or the new diet, had a sample size of 10, a sample mean of 904.6, and a sample standard deviation of 36.728. Now, we were asked if there was sufficient evidence at the 5% level to infer that the new diet yields a higher population average weight. So this implies that we are going to need to do a hypothesis test. So to begin, we're going to write out our two-lined hypothesis. And I'm going to do mu2, or excuse me, not mu2, mu1 minus mu2, which equals 0, mu1 minus mu2, and I'm going to assume that my new diet, which is my first group, is going to have a higher population mean than the old diet. Now that we've established our hypothesis, we can now begin calculating our test statistic. In order to do that, we must first begin by calculating our pooled variance. If you recall, it's that n1 minus 1, s1 squared plus n2 minus 1 multiplied by s2 squared over n1 plus n2 minus 2. If I plug in all the values correctly, and I'm a bit short on space, so I'm going to skip the plug-in part of this step, it's going to be 1,578.4. Next, we can calculate our test statistic. T equals 904.6 minus 845.5 minus 0 over the square root of 1,578.4 multiplied by the quantity of 1 over 8 plus 1 over 10. At this point, we can plug in to our calculators and we will get 3.14. This gives us our step 3, which is our decision. We will reject our null hypothesis if, remember we're basing this on our alternative, if t is greater than t alpha. We were given that our alpha value was 0.05 and our degrees of freedom is 8 plus 10 minus 2, so that will equal 16. At this point, I'm going to pull up our t table. Degrees of freedom 16, alpha value of 0.05, so that's going to be 1.7459. Now to compare, I think it's pretty obvious that 3.14 is greater than 1.7459. So therefore, we can reject our null hypothesis. Now we can go ahead and make our conclusion. At our 5% significance level, the null hypothesis is rejected. There is sufficient evidence to infer the new diet yields a higher population average weight. Very good. Okay, so real quick, I do want to go back up to slide 14. And I want to talk about why I identified my groups as I did. As I said, I like to keep things positive, and since we were trying to establish that the new diet yields a higher population average, I knew that that meant my averages for the new population were either going to be greater or approximately the same as the old diet. If you were to do things in reverse, that is perfectly fine. You would have needed to adjust your hypothesis test. Everything else would have become, or I should say, you would have had to adjust your hypothesis in step 1. Step 2, everything would have been virtually the same except for, I'm going to make this in a different color, your t test statistic would have ended up being negative 3.14. And you would have had to use, because you would have had to change your hypothesis to be less than, your rule would have had to be a negative T alpha, and your negative T alpha value would have still been the 1.7459. You just would have had to make it negative. So you're still going to get the same conclusion. You're virtually going to work with the same numbers. So it doesn't actually matter which way you go about it. Again, my personal preference is that I like working with positive numbers over negative numbers. Okay, so this last little part is going to be working with a confidence interval. We haven't done that this lecture video, have we? So we'd like to estimate the population average increase in weight with the new diet at a 95% confidence interval. So luckily, most of the information we did from our previous slides has pretty much set us up for success on this. We are going to use our formula of y1 bar minus y2 bar plus or minus T alpha over 2 multiplied by the square root of SP squared multiplied by the quantity of 1 over N1 plus 1 over N2. From our previous slides, we know that we've got 904.6 minus 845.5 plus or minus our T alpha over 2. Now this value is going to be different because when we did our critical value in our previous slide, it was just T alpha, not T alpha over 2, which means we're going to be finding T of 0.025 instead of 0.05. This is going to give us a value, if we go to our T table, 0.025, still the same degrees of freedom, and that's going to be 2.1199. SP squared, we calculated that is the 1,578.4 multiplied by the quantity of 1 over 8 plus 1 over 10. If we type things into our calculator correctly, we should have 59.1 plus or minus 39.9, which will give us a range of 19.2 to 99. Last step, as always, is to state our conclusion. And we will state that we are 95% confident that the true difference between the new diet and the regular diet is between 19.2 and 99 pounds. Perfect. All right, everyone. I think this is a good stopping point. So we're going to stop this video here. Have a wonderful evening. If you have any questions, as always, please send me an email.